Alrighty. Howdy guys. I just wanted to do like a little extra review session for you guys. That's a little impromptu. Apparently y'all's tests start on Wednesday, like Wednesday afternoon. So that's my bad. I should have known that it started. And the way I wanted to do this review is I wanted to break it up. So that's why I'm doing this one. This one is going to cover all the topics. So covering everything. Everything. That's a V. That's a V. So today's video is going to cover integration by parts, trig integrals, trig sub, partial fractions. That's right. Oops, partial fractions, rational functions, subset of the one above, and improper intervals. All right, so this will potentially be a very long video. So feel free to kind of pace yourself, or if you really want to watch it all at once, make sure you go pause right now, go fill up your water bottles, get a drink of water, go to the bathroom, whatever you need to do. All right, so the first one I want to start with is 3t plus 5 times cosine dt. And I wanted to introduce this doing the standard way of integration by parts first, and then we will move on to the tabular method. I just want to kind of show, just to make sure that everybody knows what the process is here before we start jumping to the shortcuts. So we know the integration by parts formula is given by the integral of f g prime, or I'll write alternatively later, fg minus the integral of g f prime, which you probably would have seen it, u dv equals uv minus the integral of v du, but I prefer this notation because now I can make my little chart f prime, g prime, oops, g prime, and we can go ahead and try to start filling this in. So similar to the tabular method, we need to determine which function we're going to take the derivative and which function we're going to integrate. And so to start here, the function that we're going to take the derivative of is 3t plus 5, I guess the function that we're going to differentiate. And then its derivative is 3. And then we have cosine t over 4. And doing a little bit of u sub, we get u equals t over 4. So du equals 1 over 4 dt. So dt equals 4 du. And so all of this gives us 4, and then the integral of cosine is sine t over 4. And then the way you can use this chart is we'll put these two together down here, giving me 3t plus 5 times 4 sine t over 4 minus the integral of these two terms, minus the integral of 3 times 4 is 12, so I'm going to make this 12 sine t over 4. And then you see the issue is we have to do integration by parts again, but this time it is not so bad. Pause, sorry. Pause. My mistake, got a little ahead of myself there. Not integration by parts, we're going to do u sub. We're going to do u sub again. So we get u equals t over 4. It's going to be the same process as before. du equals 1 over 4 dt. So then dt equals 4 du, giving us 48 sine t over 4 plus c. Carry down the minus, and then I'm going to go ahead and distribute the 3t and the 5. So this part here gives me 12t sine t over 4, and then this part, oops, I'll close that for you, gives me 20 sine t over 4, and then you see the constants here. We'll get basically we'll get 20 minus 48, so then this becomes 28. So then my final answer is going to be 12t sine t over 4 minus 28 sine t over 4 plus c. All right, so we're going to do another example here, this time using a tabular method. So I'm going to go ahead and write d and I. And remember, we just need to figure out which ones are we going to differentiate and which ones are we going to integrate. All right, so the immediate question is, what function do we choose for our derivative term, and what function do we choose for our integration term? So part of the reason why I like to use the f's and g's rather than the u's and v's is because integration by parts is always presented in this formula. I'm gonna block this off. It's the integral of f g prime equals fg minus the integral of g f prime. And so the easiest way to kind of determine which one is my f and which one is my g, if I make my little chart here, f prime, g prime, is which one's the easiest to integrate. And I know immediately you'd be like, well, they're both pretty easy to integrate. That is true. But one of them makes more sense because now considering their derivatives, one of them disappears. Right, so for example, if I let f be e to the 6x and I let g prime be x, what we would see is we take the derivative, e to the 6x, and we would get 6 e to the 6x, and then carries on, and then we get x, and then 1/2 x squared, 1/3, oh, sorry, 1/4, 6 x cubed, sorry, etc. None of the terms disappear, and so technically we would have integration by parts forever. Now, on the other hand, I use x, and then e to the 6x is my integration term. The derivative of x is 1, and derivative of a constant is 0. And then here we get 1/6 e to the 6x, and then 1/36 e to the 6x. And so my point is, to all of this, we get a nice like end to our integration by parts, because again, if we did 36 times 6 would be 36 plus 180, to 16, I think, e to the 6x over 1. Right, now our term matching the tabular method, we would go, I'll use purple. These two functions, oh, then we have plus, minus, plus, minus. These two functions minus these two functions plus these two functions, and you'll see that gives us x e to the 6x minus 1. Don't have to multiply anything by 1 over 6 e to the 6x plus 0 times 1 over 2, 16 e to the 6x. This cancels, and this is our final answer. Whoops, missed a 6. This is our final answer. There we go. Did I miss something? Yes, I did. 1 over 6. Final answer for real this time, 3rd time's the charm. And so my whole point to that was it's not particularly obvious what your integration and your differential plus c. All right. And so you might have been asking, well, how do I choose? And there's 2 forms that this acronym is usually presented. The first one is the IATE or ILATE. The reason it's given in 2 forms is because in those examples or in those cases where these 2 are involved at the same time, it's kind of hard to choose. But you don't have to worry about it too much. You will probably likely be here. Really, the best way that I could explain what this acronym is for is determining what function goes here and what function goes here. And so you basically, you have logarithms, inverses, algebraic expressions, trig functions, and exponential functions. And it goes like this. And so it's basically just helping you determine which one is going to be your derivative. But again, you have to be careful because sometimes, right, these forms don't always work. But don't worry about that right now. So the reasoning that I used to determine my D here was that it was an algebraic term. So I put it there in the D column versus my exponential term takes the lower end of the priority here. So we know that it was going to go in here. All right, so the next example we're going to look at is sine of x over 3 times e to the x, e to the 2x, sorry, dx. And I'm going to set up my di, or my d, yeah, di. di. And remember our IATE. All right, so in this example, we're here. So I know that t comes before e for my derivatives. So I'm going to put sine x over 3 here, and then e to the 2x. I'm going to integrate this one a few times, so then I get 1/2 e to the 2x. 1/4 e to the 2x. 1/8 e to the 2x. And 1/16 e to the 2x. X. And I'm going to move this over because I'm not going to write it. All right. And then the derivative of sine x over 3, third, sine x over 3, 1/9, sine x over 3, 1/27, sine of 3. And then I'm going to stop it right here. Stop our table right here so that I could point something out. We could technically do this infinitely. This could go on forever, and this could go on forever. And good catch, thank you. Boom. Boom. Cosine. Bonus points on your exam if you caught that. I'm just kidding. I have no authority to do that. Don't take that serious. Negative sine, negative cosine. And then we've got plus, minus, plus, minus. Go ahead and start circling things. So we could go on infinitely, but the point I'm about to make here is that the coefficients play a big factor on how much each function or each like part of the function influences the overall. The overall function. So if we look here, we're just going to have one half sine of x over 3 e to the 2x minus 1/3 times 1/4 is 1/12 sine x over 3 e to the x times 2. And then plus, but we've got a minus, so then it's minus. Oh, and I did it again. I'm sorry. I've been having this problem for whatever reason. Cosine. And then our next term is going to be minus 1/72 sine of x over 3. And then one more time. This we've got a minus and then another minus, making it a plus. Plus. I believe this was 1/473 cosine x over 3 e 2x. Three, 16, 0, 7, 2, 4, 3. Didn't think that was correct. 33. There we go. You see, we've got coefficients that get smaller and smaller and even smaller. So if we were to keep going, which we could, we would get 81 times 32, which is an even small number. I think it's in the thousands, making this next term of 1/2 something sign pretty meaningless. And so we can actually, if you wanted to, cut it off right here, which would be one term, do it in green here. One term, two term, three term. We didn't even need this part. So yeah, I'll leave that as an exercise for you guys if you want to see why sometimes the tabular method actually just causes more work. In this case, you would use the natural log of x as your derivative term, and the integral term here as 1. We're going to put an artificial 1 right here. This time I'm just going to use the capital F prime, G prime. And since we're taking the derivative of natural log of x goes here. And 1/x goes here. 1 goes here, so then x goes here. And then I'm going to go here. And then take this to be x, natural log of x, minus the integral of this, which is 1. 1 dx, which gives me x natural log of x minus x plus c. And if you do this method here, take 4 derivatives and write out the expansions. Make sure you guys double check your coefficients, do your derivatives correctly, etc., etc. You will get this. Just takes longer. But again, looking back at the acronym, the ATE, we know that the term that's going to be our derivative goes in this order, where this is the highest priority versus this one. For the differentiation term, differentiation term. So in this case, we are here and here. So logarithms come first, and then algebraic expressions, giving us this chart. But again, this method here is much fewer steps. But you're more than welcome to stick with this if this is what you're comfortable with at this point. But try it. You'll see what I'm saying. All right, so we are moving on to the next example, and we're moving on to the next topic as well. So this is integrals with trigonometric functions. So the first one we're going to look at is sine to the 5th x dx, the integral of sine to the 5th x dx. So the first thing we're going to do is I'm going to break off a sine. X times sine of x dx. And as you guys know, this topic involves trigonometric identities and taking advantage of them when we need to reduce some of these powers or deal with some of these powers. So the first trig identity I'm going to use here is sine squared x equals 1 minus cosine squared x, which comes from the Pythagorean theorem. If we do some algebra on this, we get 1 equals sine squared plus cosine squared. And so here, right, I can rewrite this as sine squared squared. So rewriting this below, I get sine squared x squared times sine of x dx. And then using my identity here, I'm going to substitute the parentheses, giving me 1 minus cosine squared squared x squared sine of x dx. Okay, and then doing u substitution, I'm going to leave that part, the intermediate steps, to you guys. This will give me the integral 1 minus u squared squared du. And then foiling this expression, this is really 1 minus u squared times 1 minus u squared. Foiling this out, this gives me the integral 1 minus 2u squared plus u to the 4th. And then carrying out this integral, we get u negative u minus 2/3 u cubed plus u to the 5th over 5. And then remember, our u was cosine. So now we get negative cosine cosine x, yep, x minus 2/3 cosine cubed x plus 1/5 cosine to the 5th x plus c. Alrighty, the next example we're going to look at is the integral of sine squared x times cosine squared x. And so this time the two identities that we're going to be using are cosine squared x equals 1 plus cosine 2x over 2, and sine squared x equals 1 minus cosine 2x over 2. Okay, and so substituting these into my integral, I get, back at it again, 1 plus cosine 2x 2 times 1 minus cosine 2x over 2. Multiplying these expressions, this gives me 1 minus cosine squared, it's not 4x, x over 4. This just comes from foiling here, 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 and here. And then we're taking the integral of this. I can take this out of the integral. So this gives me 1 over 4 integral 1 minus cosine squared 2x cosine, and then since we know cosine squared x equals 1/2 1 plus cosine squared x 2x, if I have cosine squared 2x, this just becomes 1/2 1 plus cosine squared, and then 2 times 2x is 4x. So I'm going to go ahead and substitute this in for my integral there. The integral of 1 will give me x, then I'll have 1 over 4 x minus the integral of 1/2 sorry. One plus, sorry. Dx, or close this bracket here. Not yet. We're not done yet. This is dx. What we see is we're going to get kind of a cascading integral that we're going to continue to have to substitute this value in. Or what I can do is I can just cut it off here. I would basically take sorry. Wouldn't have to cut it off here because we can do this integral. Okay, so doing this integral, we get 1/2 x plus 1/4 sine of 4x plus c minus x 1 over 4. Nope. There we go. And then cleaning this up, we would get x over 8 plus sine 4x over 32. This is minus of this plus c. Alrighty, so we're going to move on to trigonometric substitution. And this example still kind of coincides with the one from before. So yeah, so let's get into it. So the integral that we're presented here is given in the form a squared minus x squared, where we'll be using the substitution x equals, let me just double check. Excuse me, yep. A sine of x. All right, so what we're going to do is I'm going to substitute this in, where in this case a equals 3, because these two correspond. We take the square root of 9, we get 3. So then I have the integral 9 minus 3 sine theta, squared. And then dx, what is our dx term? If we look back up here, in this case, x equals 3 sine theta. So if I take this derivative, I get 3 cosine theta d theta equals dx. So I'm going to substitute this dx term, giving me 3 cosine theta d theta. And then what I can do is I'm going to go ahead and send this one in. So this gives me square root of 9 minus 9 sine squared theta, 3 cosine theta d theta. I'm going to pull the 9. I'm going to factor out a 9 from both of these expressions and then pull it out of the radical. So that gives me the integral 9 sorry. Yep. 9 1 minus sine squared theta. And this 9, if you're confused, remember we have this constant 3 just sitting out here. So when you pull the 3 out, you multiply that by 3, it gives you 9. And then we have an identity for this. We have an identity for this expression. Remember, it is cosine squared theta. So rewriting this expression, we get integral of 9 root cosine squared theta times cosine, cosine theta d theta d theta. Cancel. This gives me the integral of 9 cosine squared theta, because when I cancel this radical and the square, it leaves me with just cosine times cosine theta, which gives me cosine squared d theta. And then what we're going to do now is I'm going to go back and I'm going to substitute this expression for 1 minus sine squared theta. And Damn, unlucky. Unlucky. Lose my chair, I promise. Giving me 9 times 1 minus sine squared theta d theta. Pulling the 9 out, I get, and then I'm going to go ahead and carry out the integral. All right, and then so for this step, we know that we have an identity for this. Ignore this, sorry. We know we have an identity for cosine squared, and the integral for cosine squared is equivalent to 1 plus cosine 2 theta over 2. So pulling that 9 out, I get integral of, I'm also going to pull out this 1/2, put it right here. And I have 1 plus cosine 2 theta. Carrying out this integral, I get 9 over 2 x plus 1/2 sine 2 theta. Then just to clean this up, I'm going to get 9 over 2 x plus 9 over 4 sine 2 theta. And then, oh, I'm sorry, this is theta, not x. Theta, theta. And the last thing we need to do is we need to substitute in our theta, given from this expression here, x equals 3 sine theta. What we can do is we can isolate theta, and I'll do that down here. We can isolate theta, giving me x equals, break the pen, x equals 3 sine cosine sine, just making sure, sine theta. Then I'm going to take divide by 3, so it gives me x over 3 equals sine theta. And then I am going to multiply, is that what this is called? Multiply by sine inverse, giving me theta equals sine inverse of x over 3. And then substituting in my theta, I get 9 over 2 sine inverse of x over 3 plus 9 over 4 sine of 2 sine inverse x over 3. Alrighty, so the next example we've got here is the integral of 1 over x to the 4th square root 9 minus x squared. So similar to the last example, we have our function presented in the form of the root of a squared minus x squared, where in this case a equals 3. So in this case, x equals sine times 3 theta, yep, theta. So similar to the last example, I'm going to go ahead and substitute this in. So this gives me, then I'm sorry, we're going to have dx here. So then my dx term, we're going to go ahead and solve for that, is 3 cosine theta. So first thing that I can do to simplify is pull this out. Which gives me Real quick, not to like skip too many steps, but again, similar to the last example, once we substitute in x, we're going to have two factors of 9, which I'll be able to pull out a 3. So this is really 3x to the 4th square root 1 minus already substituted in. I'll go ahead and do that. Sine squared theta. I'll substitute the x in a second. I just kind of wanted to emphasize this is where that came from. We already factored out that 9. And then d theta would be, I'm sorry, dx is 3 cosine theta, d theta. So cleaning this up, we get 3 cosine theta, d theta in the numerator, d theta, times we get sine to the 4th, and then 3 to the 4th is 243, right? Sorry. 3, 9, 27, 81 times 3 is 243. 243 sine to the 4th theta times, and then remember this reduces down to cosine squared theta, giving me cosine theta after canceling the radical. Okay, cool. So we see that we can cancel some things. I'm going to cancel, and then I'm actually going to reduce this. So then I'll be left with the integral 1 over, oops, not there yet, 1 over 81 sine to the 4th theta. And we know that the reciprocal of sine theta is cosecant theta. Oops, cosecant. So I can go ahead and substitute cosecant in, and then gives me 81 cosecant. Sorry, not 81. 1 over 81 cosecant to the 4th theta. And then, so similar to how we have trig identities for sine and cosine, we also have identities for their reciprocals. And we actually have an identity for cosecant squared. This identity equals 1 plus cotangent squared theta, not cosine, cotangent squared theta. And so what I'm going to do is I'm actually just going to split this apart, giving me 1 over 81 cosecant squared theta times cosecant squared theta. I'm going to substitute one of these terms in as 1 over cotangent. So then this gives me 1 over 81, 1 plus cotangent squared theta times cosecant. And then what I can do here is I can do u sub, and then I'll do this one for you guys. My u term is going to be cotangent theta, so the derivative of cotangent is negative cosecant squared theta d theta, meaning, oh, this has a d theta here. So d theta equals 1, du over negative cosecant squared theta. So substituting these back in, I get the integral of 1 over 81, 1 plus u squared, and then cosecant squared over negative cosecant squared theta du. Cancel, we still have our negative sign, so I'm going to pull it out, giving me integral of negative 1 over 81, 1 plus ln squared u. Carrying out this integral, I get negative 1 over 81, u plus u cubed over 3 plus c. Now remember our u term was cotangent, so then I get negative 1 over 81 cotangent theta plus cotangent cubed, not cosine, cotangent cubed theta over 3. Now we need to solve for theta, going all the way back up here. We're going to solve it the same way we did the other time. I'm going to bring this down. If x equals 3 sine theta, then theta equals sine inverse of x over 3. So substituting this value, mosquito, 1 second. Gotta focus. Unlucky, he's under my desk. That's 2 more mosquito bites for him. Yep, so substituting this back in here, we're gonna get 1 over 81, 1 over 81, cotangent, not cosine, cotangent, sine inverse, x over 3, plus, making sure my parentheses line up where they need to, cotangent cubed, sine inverse of x over 3 over 3. And then we could reduce here because this is no, never mind. This would be your final answer. Yeah, we're not going to get into that. All right, so the next example, we're going to move on. We're going to move topics now. We're going to move to partial fraction decomposition, or rational functions, depending on how you look at it. So the first thing we want to do to approach this problem is we see that we have a polynomial term in the bottom. We have 2 polynomials, but we have a quadratic polynomial in the bottom. And this can be expressed as 3x over x plus 1, x minus 2. And from y'all's lessons, y'all know that when you decompose a fraction, or I'm sorry, you decompose a function with the denominator looking like this, we get the form a over x plus 1 plus b over x minus 2. And what we can do is we can cross multiply and set up a system of equations. So what this does is this gives us 3x. So we're solving for this term up here. So 3x equals a x minus 2 plus b x plus 1. And then distributing our constants, we get ax minus 2a plus bx minus b, or plus b, sorry, equals x. And then what I see here is I have an ax and a bx, and then an a and a b. So what I have now, kind of manipulating this expression and then pulling out constants. I'll show that to you guys. So we get ax, rewriting this expression, plus bx minus 2a plus b. And then what I can do is I can pull out an x from this term, and then there's nothing to pull out from this term. So that gives me, I'm actually going to switch these two though. So that minus sign stays attached to the 2a, which now rewriting this, I get 3x equals a plus b x plus b minus 2a. Right. Next thing I want to do, I want to recognize the form that we have on both sides. Right, so over here we have a 3x, and over here we have an a plus bx plus b minus 2a. So this kind of tells you that this might be an extra term because we don't have a variable attached to these parentheses. So what I can do is I can assume that a plus b equals 3, meaning that b minus 2a must equal 0. And then what we can do is I'm going to rearrange this so that b equals 2a, and then I can substitute that in over here. So then I get a plus 2a equals 3. So then solving for a, I have 3a equals 3. So then a equals 1. I want to substitute that back over here. B equals 2 times 1. So b equals 2. And then back up to our original expression here. I'm going to pull this down. We get the integral, do this in black, integral of a over x plus 1 plus b over x minus 2. Substituting my a and b, we get the integral of 1 over x plus 1 plus 2 over x minus 2. And then from here, we should know how to integrate this. So carrying this integral out, we get natural log x plus 1 plus 2. I don't need this integral sign anymore. Sorry. Natural log x minus 2 plus c. All right, so the next example we're going to look at is the integral of 3x plus 2 over x cubed minus x squared minus x, or 2x. And so what I'm going to do is I'm going to rewrite that bottom polynomial over here, and we're going to factor it. I'm going to show you guys that algebra. X cubed minus x squared minus 2x. What I can do is I can pull an x out. So I have x squared minus x minus 2. I think. Yep. Exactly what I thought. So what we get here is we get x plus 1, x minus 2. And then so what I'm going to do, I have 3x plus 2 over x plus 1, x minus 2. And from your classes, you'll know that this decomposes into a over x plus b over x minus 2 plus c over x plus 1. And then so we see that we have 3x plus 2 equals a x minus 2 x plus 1 plus dx x plus 1 plus cx x minus 2. And the way we get there is I'm going to find a common denominator. So I want my common denominator to be this expression. And then so by multiplying x plus 1 over x plus 1 and x minus 2 over x minus 2, here is x over x, and then x plus 1, x plus 1, and then here is x over x, and then x minus 2, x minus 2, minus 2, fraction, 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 and fraction. This whole thing gets you here. And then, so this we know equals x squared minus x minus 2. So then I have a x squared. I'm actually just going to write this so we can see the next step. A x squared minus ax minus 2a plus, then we have bx times x is bx squared. Bx times 1 is bx, and plus cx squared minus 2cx. I'm going to rearrange it so I have my powers all together. So then I have a x squared plus bx squared plus cx squared minus ax plus bx minus 2cx and minus 2a. Doing a little bit of factoring, I'm going to factor here. I'm going to make this factor here. Then can't really factor here. I'm going to have x squared, a plus b plus c plus x negative a plus b minus 2c minus 2a. And then solving the system of equations, the way we set this up, we have a 3x plus 2, right? So then we get, this is how I did it in differential equations, just to give you guys a look, a little tip on something I used to do. So we have an x squared column, we have an x column, and then we have a constant column here, constant here, right? And we don't have an x squared term here. So then I have a 0 equals, and then I have a linear term, 3x, and then I have the 2. So then I have 2, and then I'm going to substitute these values here. This one here, and this one down there, giving me negative 2a, negative a plus b minus 2c, and then a plus b plus c. From this area, we have 2 equals negative 2a. So then a equals negative 1. A equals negative 1. I'm going to substitute that into anything, really, to be honest. I could substitute it into, oh, I'm sorry, this is not 3x, this is 3. Substitute it into here, which would give me negative 1 is 2. Move that to the other side. Okay, sorry if I misspoke. This is negative 1, which is positive 1. Move that to the other side, so then we get 2 equals dividing bar b minus 2c. Okay, that doesn't really help us. So maybe I'm going to plug this into here, giving me, and then following the algebra, we get 1 equals b plus c. And then I'm going to move either b or c to the other side. Let's do b, so that I have c equals 1 minus b. I'm going to substitute that here, giving me 2 minus equals b minus 2 minus 2b, which gives me negative b minus 2 equals 2. Isolating the b, moving this to the other side, I see that, sorry, minus 2b, so then this becomes a plus. And then we actually have 3b, sorry, pay attention to your signs. Moving it over, we get 4 equals 3b. So then b equals 4 over 3. And then the last thing that we can do is I can take this term that we kind of already isolated, c. Then I have c equals 1 minus 4/3, which means c equals negative 1/3. So after all of that, I am going to bring down our original expression, which was a over x plus b over x minus 2 plus c over x plus 1, substituting in a, b, and c. A, B, and C. A is negative 1. B is 4 over 3, so it's 4 times 3. 3. And then negative 1 times 3. And then we're going to integrate these terms with respect to x. So this is our final decomposition form. The system of equations might take a second, but it's really just algebra. The easiest way to set it up would be kind of like this. We have a little, we have our quadratic terms, our linear terms, and our constants. And the reason that's what we did up here, we have x squared for our quadratic terms, x for our linear terms, and we have 2 here for our constant terms. And that all comes from this part, setting them equal to each other, setting the numerator equal to the expression that we found here. And then ultimately we are here, which is just the integration step. So then we get the integral of the, don't need that, negative ln x plus 4/3 ln x minus 2 minus 1/3 ln x plus 1 plus c. Alrighty. So the next one we've got is the integral of cosine over sine squared x minus sine x. And the first thing I'm going to do is I'm going to do a little bit of u subs so that we can set up this integral in an alternative form. And by doing so, I'm going to let u be sine. And so this substitution gives me du over u squared minus u dx. And then I can pull out a u, giving me du over u minus 1. Okay, so then using our partial fractions, this decomposes into negative 1 over u plus 1 over u minus 1. And again, I'm sorry, a and then b, a and then b. And then the nice thing about this equation is that the system of equation actually just breaks down to where we have a equal 1 and b equals 1 as well. You can verify that by, cross multiplying and then setting up your system of equations. So then now we have the integral of negative 1 over u plus the integral of 1 over u minus 1. And then we get negative ln of u plus 1 over u minus, natural log u minus 1. And okay, substituting in my u, we see that we get natural log of sine of x plus natural log, I'm sorry guys, minus 1 plus c. All right, so on to the next topic. The next topic is covering improper integrals. And so the first example we have here is the integral from negative infinity to 0 of 1 over x squared plus 4. Ooh, sorry. Okay, ooh, man. Like 3 or 4 hours into this, I didn't really check to see if my mic was on. Sorry. So what I can do is I can actually change, just let this value be t, and I can pull that infinity out, and I can say I want to look at the limit as t approaches negative infinity of t to 0 of 1 over x squared plus 4 dx. And so we should know that this integral gives me tan inverse x over 2 times 1/2. And again, we're still taking the limit as t approaches negative infinity on the bounds from t to 0. And then, so mosquito, where'd you go? Okay, sorry, mosquito is taunting me. This gives me the limit as t approaches negative infinity of 1/2 tan negative 1 of 0 over 2 is 0 minus 1/2 tan of negative 1 t over 2, which just gives me the limit as t approaches negative infinity of negative tan 1/2 tan inverse of t over 2. And then we see that this converges to pi over 4. I'm sorry, we take t to negative infinity, and that gives us pi over 4. Alrighty, and because I have to get up in like 4 hours, 5 hours. I don't know, it's 11, 6 hours, 6 hours. The last problem we're going to do here is negative infinity to infinity of x e to the x dx. And because I have my bounds from negative infinity to infinity, I can actually break this up as the integral from negative infinity to 0 x e to the x dx plus the integral of 0 to negative infinity of x e to the x dx. Okay, so I'm going to do the left-hand side first. So left hand, we take the integral from negative infinity to 0 of x e to the x dx. And by integration by parts, we get, I'm sorry, first dealing with the bounds. Rather than having negative infinity to 0, I'm just going to take t to negative infinity, so then I get the limit as t approaches negative infinity of the integral of t times 0 of x e to the x dx. And then here, by integration by parts, this gives us a limit as t approaches negative infinity of x e to the x minus e to the x on the bounds from t to 0, giving me the limit as t approaches infinity, negative infinity of t e to the t. Oh, sorry. Not quite. This substituting in 0 here gives me 0 minus 1. So then I have minus 1 and then minus t e to the t minus e to the t. Minus minus is a plus. Then we take t to infinity. We see our negative infinity, rather, this goes to negative infinity. But this goes to negative infinity. This goes to negative infinity. So this converges to 0. This converges to 0. Leaving us with -1 for the left-hand side. And then for the right-hand side, I get the integral of 0 to infinity of x e to the x dx. And I'm going to do the same thing. Rather than having an infinity here in my integrand, I'm going to take it out, replace it with t, and then take the limit as t approaches that value, which in this case is infinity. So then I have the limit as t approaches negative infinity of the integral of 0 to t x e to the x dx. And again, by integration by parts, this yields the limit as t approaches not negative infinity, positive infinity of x e to the x minus e to the x on the bounds from 0 to t. This gives t e to the t minus e to the t minus 0 minus 1. All right, so minus 1 is plus 1. So then now this gives me the limit as t approaches infinity of t e to the t minus e to the t plus 1. I take all of these expressions to infinity. This goes to infinity, this goes to infinity, this goes to infinity, this goes to 1 because we're not taking any limits. So I know that this diverges to infinity. And because the right-hand side, oops, not the wrong number, sorry, I have it. Since the right-hand side diverges to infinity as t approaches infinity, I know that the expression, the original expression, negative infinity to infinity of x e to the x dx diverges to infinity for all x, I guess. We know that it diverges. And so, yeah. I'm gonna take me a second to edit this, so I'm sorry that this is gonna go out so late, but I hope this helps. This was kind of an impromptu review session, so I apologize if it was a little rough. But hopefully I'll see you guys tomorrow and Wednesday. I guess today is Monday as I'm recording this, so hope to see you guys Tuesday and Wednesday. Good luck on your exam. Study hard. Don't stress. Best of luck. Goodbye.